So, welcome to another interview. It's been a little while since I've done one of these, and I saw some great designs coming out of the IEEE chipathon. So, I reached out to Jorge, and he very kindly accepted my invitation for an interview, and we're going to hear about his project today. So, um, welcome, Jorge. How are you doing?
Hello, Matt. I'm doing fine, and you?
Yeah, I'm good. So, you're based
Right.
in Chile, right?
Yes, we're here in Valparaíso, Chile. Yeah, it's
And
seaside
how did?
city.
Yeah, me too, in Valencia. So,
It's
yeah,
great.
I'll have to take a boat ride one day.
Whenever you want. Yeah.
Yeah. No, it's a country I'd love to visit someday. So I'll take you up. I'll take you up one of these days.
Great, great.
Tell us a little bit about yourself.
Okay, so yeah, I'm postdoc researcher here at AC3E Center in Valparaíso. Um, Previously, I was living in in Belgium for quite some time, around 10 years, and I did my PhD there, and I had brief industry experience, and I was working in chip design, focused on mixed signal chips, basically, mainly sensor interfaces. So yeah, I was looking for opportunities here in Chile. As you may know, in our countries, since we're so far from the places where these things are produced and were invented, these technologies, it's hard to find jobs. There's no industry here yet. So, but yeah, this I found this postdoc position. I had a good match with a professor here, with Cristian Rojas, and we've been working together in this project. He's from the power electronics side, so we are trying to merge these two visions: the microelectronics and power electronics.
So you have plenty of chip design experience already.
Well, I did my PhD and then I was briefly working in an industry. I wouldn't say it's a lot of experience, but yeah, I've done some chips and
Yeah.
we managed to publish them.
And was that always using proprietary tools before this?
Yes, it was
Okay,
mainly
interesting.
focused on that.
Yeah.
Yeah.
Yeah. So, like I mentioned in the intro, I saw a post from you. I mean, I was following the IEEE chipathon. I think this is the second time they've run it,
Yeah,
and I
it's
was kind of
second time.
lurking in the Slack channel, and I did a presentation early on about the work that I've done with my multi-project stuff and the tiny tape out stuff.
Yeah.
And I saw your design being featured on LinkedIn, which was for a DC to DC converter, and it looks really interesting. I really like finding out more about mixed signal style and analog style projects. So I was really happy that you accepted my
Mm.
offer of an interview. Um, so maybe you can tell us a little bit about your experience with the IEEE Chipathon. Give us a little bit of an overview of what that is, and then
Yeah.
maybe we can talk about your design.
Yeah, sure. So the chipathon is an international program competition. I don't know how we can put it, where you can send your project proposal for a chip design. This was done around May, I think, 2022, and you get your project evaluated, and then there were 50 projects, I think, and half of them were selected for the program. And then you get into this mentoring program, which is really cool. You have weekly meetings with the people who organize this and with other assistants, let's say. The main researchers who are working here are Boris Murman and I think Mehdi Saligari.
Yeah,
Both,
yeah. So I've had a chat with Mehdi already, and I'm actually due
cool.
to talk with Boris in the next week.
That's
And
great.
just in case people didn't know who's watching the video, Boris recently released free a book that he published. I think it was maybe 5 or 10 years ago, and it's no longer in publication. He's very kindly released that into the public domain now. So if you're want to
Yeah.
learn more about analog stuff, then check out that book. I'll put a link down in the description of the video after this.
Yeah, no, it's great. They're sharing really a lot of open material and resources. So yeah, one of the instances is this chipathon, and then yeah, while you go into this mentoring program, of course, you need to start designing your chip, and then there's a tape out hard deadline, and
and they go for so the IEEE pay for a chip ignite slot
exactly.
for a bunch of people, don't they? So you're guaranteed once you're selected into the program.
Exactly.
Yeah, I really like that because it's a great way of kind of making sure that we see like high quality, well documented, tested designs coming through that we can all benefit from.
Yeah, no, it's definitely a very interesting way of getting more building blocks into the open source community.
Mm-hmm.
And yeah, the criteria to be selected is to have your tape out done. So that's a very objective way of knowing that a design is, you can fabricate it and you passed all the pain in the tape out phase. After the design.
So did you tape out on the 5th of December, that the Chip Ignite Q3, yes. Q4 2022? Yeah, okay.
Yeah, for that.
Yeah, good. I'm on the same one.
Okay, yeah, I think I saw your design too.
Yeah. So how did you find the way that the project was organized, the IEEE Chipathon?
Yeah, I really liked it. Well, actually, this was maybe a bit differently to other projects in the chipathon. This was a fully student project. So I was just like coordinating and doing some like high-level simulations and stuff like this. But there was a lot of student work, and I was trying to motivate them all the time to go to the mentoring sessions. Of course, they are students. They have classes, and it's hard lives. For them to. Yeah, they have lives too. Yeah, exactly. So not all of them could attend, but some of them could see the videos afterwards. But they were really involved. And if I think about myself at their age, it would have been great to have this experience, this amount of knowledge, like a big, huge brick of knowledge in 6 months,
and having access to the tools as well. So
that's right.
Maybe before I forget, so we'll talk about your design in particular, but I'm just interested to get your feeling, because you said in the intro you're living in Chile. It's far away from the kind of center of innovation and where the chips are actually made. And one of the things I am excited about the open source tools is, I mean, it's easy to say and it's like a buzzword, but the democratization, the lowering of the barriers to entry. And I think that even people who are paid, who their job is to design chips, they don't actually get to design what they want to design. They're told what to design because the access to the tools is so expensive. What is your viewpoint on how having access to chip design tools is going to change the landscape in the semiconductor industry in the next 5 or so years? I understand that's a huge question.
Yeah, I can humbly try to give my point of view. Well, when I left Chile in 2010 to go to Belgium, there was definitely no way to have access to commercial tools, at least for the analog flow here in Chile. We had some licenses from Synopsys, because there's a Synopsys office here in Chile. But for the analog tools, I mean, the commercial standard, it was impossible to get these things. Not to talk about the PDKs and all the knowledge also that you need to start doing these things. So that's one part of it, like what you mentioned, the democratization. But then, which is really important, of course. So if it was not, if we didn't have this, it would be impossible to try to start some design team here. But also, what is really relevant is are the automation capabilities that can be enabled with this open approach. Currently, with the industrial tools, I think it's really hard, and well, I don't know.
You have to have your own private data center, basically, don't you?
What? Sorry, I didn't get it.
You have to have your own private data center so that you can run everything like in an isolated rack of service.
and it's not well integrated. I think it's hard to integrate. I worked for 2 or 3 years in IC design companies, and you can see that many processes are still very manual, like in analog mostly. So that's a huge amount of time that you waste doing things.
Easy to make mistakes as well.
Also, same, exactly. You can have a lot of issues. The reusability is really low. So even if you do the same project, you many times need to start from scratch or similar projects. So I think these two aspects are really relevant. It's going to be a big change, I hope. And I think industry will also try to catch up. So that's also good. I like a lot what Boris says about the way how we circuit designers used to work and how it will be in the future. Until now, it's like really closed. You are in a basement room, closed, NDA protected. It's quite terrible to work like this. It's quite boring. So this fresh air of open technologies, open PDKs, open tools, it's great to have it.
Yeah. Are you mentioned you're supervising students. Are your students excited, or do they kind of not really realize the opportunity?
I think some of them realize about the opportunity, there have been some initiatives here in Chile to start some design groups. It has been super hard. Actually, in this university, they used to have some design courses 15 years ago, and then the professor who was teaching this, he left. So that's the terrible part here. If the person who brings this leaves, then you're done. You can't continue. Other universities have also tried to start this. Some of them with successful starting some groups. Design groups, but the knowledge here from the student point of view is really we don't have design courses. I see design courses, so they can't get the complete story in their heads. But I think some of them they see the final the point here, and some of them are super motivated, and I would say much more people that I was expecting. Actually, when we started the chipathon project, we sent an open call to anyone who wanted to join, like no restrictions, undergraduate, graduate, whoever wanted to join. I thought there would be a couple of students interested coming. Okay, we will try to do a small project, la la la. Then we had 11 students interested. Of course, not all of them finished the project, but still, I think they all contributed and they all got something from it. So it's great, I think.
Yeah. We'll see what. It's always interesting, like when a change is coming, there'll be some people that realize it and like they're excited about the change, but then there'll be like the people that come up after them where they just take it for granted. It won't even be different. It will just be how it always was. So
Yes.
yeah, then those people kind of are more freer to innovate because they're not kind of trapped by the existing framework that everyone else is
Flows.
used to. Yeah. So maybe now is a good time to move on, and you can show us a little bit about the design that you submitted.
Okay, great.
So I'm going to put your screen up, maybe like this. Yeah. You said you didn't want to talk through the slides, and it's probably a good idea to just like highlight some of the things that you think are most interesting.
Yeah, I'll do that. So I just wanted to show a picture of the team.
Of the team, yeah.
Small. So we had 11 students working on this, plus Christian, who's the professor with whom I'm working, and myself. And we try to also give a nice motivation to the project. So this is a DC-DC converter, but we're here trying to grab some specs from CubeSat EPS systems. So CubeSats are these 10 by 10 by 10 centimeter cubes that you can send to space as small satellites. There's some experience here in Chile with these CubeSats, so our final aim would be to try to send our chips on one of these CubeSats.
Yeah.
Of course, it's a double risk. Like developing a chip is huge risk. Doing a CubeSat is the same, and then putting them together is like you multiply the probability of these two. So, but yeah, it's something that is quite new. So we are trying to go on that path. Basically, we started focusing on the.
Can you imagine telling yourself as a child, like in the future, you'll be designing chips that go into satellites? You wouldn't have believed it.
No, definitely. It's not something that we commonly do here in Chile.
Or anywhere else.
Yeah, that's true. So a bit about the system. The full system includes the photovoltaic cells conversion to a DC bus, and then from this, batteries connected to the DC bus, and then from this bus we have outputs to 3.3 and 1.8. We initially focused on this part of the EPS, but then we realized that the high voltages in the PV cells were compatible with the basic topologies that we wanted to try. We didn't want to go into difficult topologies that we didn't understand. So we tried the most basic, and that's why we moved to this side of the EPS. So between the DC bus and the lower voltages. When we tried to start designing, we were trying to find a starting point, and we found a really good one, which is Weston Brown's project.
Yeah.
I don't know if you have seen this.
He's on the list to interview. We've tried to do it at the Hackaday Supercon, but it was too busy.
Okay, yeah, I can imagine. I think he's doing his PhD. So, but he has a very, very nice DC-DC design, open blocks. It includes also, actually I have here his slides. You have the GitHub, which has a lot of information. And then, you have the chip, which includes the control circuitry, of course, debugging and the power circuitry. We focused on the power circuitry, and we took some of part of his design as an input for our design. Actually, we used his switches, the switches he designed. We included them in our system. So, but we try to move a step forward, of course, and we focus on this 3-level flying capacitor converter. We have a schematic of this here. So it has 3 main blocks, we could say. So we have the switches, right, which have which toggle and move the connections of the capacitor in different ways. And then we have the flying capacitor, okay, which we decided to do as an integrated capacitor, which is something that I think outside of this chipathon would be impossible to try because it's a huge area. And then we have the gate drivers, which condition and manage the currents that are needed in the gates of the switches. This is what we integrated on chip. So we have that this as one of the cores, and then we have two of these cores which are interlinked, operating in an interlinked way. So on the right side, you can see the chip, the final GDS that we submitted.
Yeah, maybe you can zoom into that image a bit so we can see it a bit better.
Yeah, so this is the layout of our chip. You can see that the active area is quite small.
Okay, and you're using Caravan here, I take it.
Yeah, it's a Caravan.
You can see, because if people aren't familiar, we've got two ways of applying for the shuttles: Caravel and Caravan. And Caravan is like more for analog, and it's missing the top row of IOs. So if you want to get kind of completely uninterrupted access to your design, you can put whatever you want up the top there, don't you? So I can see you've got a couple of weird looking pads up there.
Yeah, actually we had to hack a bit this this whole thing, because we are targeting here 300 milliampere currents per core, so it's total 600 milliamperes, and the Caravan is not designed for this current levels. So we have a low current operation mode, which works through the normal paths, which, as you said, they don't have ESD, so it's basically a piece of metal connected to the user area. And then we have also some extra pads in the user area that can be bonded externally to the package or to a PCB. So the active area includes, it's mirrored here. So on the left side, you can see the 4 switches. The gate drivers are too small, so you can't really see them. And then the right side is for the second core. This huge rectangle here, as I mentioned before, is the
capacitor.
Cap. Yeah, that's the flying cap. So it's 2 min caps stacked. So the metal 3 and metal 4 min caps. You have this option in Skywater, 130 nanotechnology. Still with these two caps, the density was quite low compared to what we needed for the operating frequencies of this converter.
I guess that's one reason why people like high frequency converters, so that the caps can be smaller.
Yeah, exactly. Yeah, you can scale, you can gain in area. But actually, the designs that we reviewed in literature, most of them have off-chip flying caps.
Yeah.
And actually, we left here these 2 pads which allow to connect off-chip some discrete component capacitor in parallel to this.
So will you get bare dies back then as part of the chipathon?
Yeah.
Okay. Then you can wire bond out some extra caps if you need to.
Yeah, that's an extra problem we're getting in, but we're figuring it out how to do it and who can help us with this.
Okay. Yeah, I've got some wire bonding contacts. I'll be happy to introduce you.
Okay, that's great. Great to know.
And the structures lower down the net, are they all inductors?
Yeah, we have some inductors here because we designed this, or we tried to design this to share the Caravan, because that's also part of the aims of the objectives in the chipathon, to be able to to work with other teams and to integrate as many designs as possible inside the user area. But after a while, we realized that due to pin limitations, it was very difficult to share with other teams. So this lower area was supposed to be used by another project, but then we decided to get some inductors, mainly for characterization, because they're still a bit low for what we would need if we wanted to use them here. But just to have an evaluation of what we have, because I think there are some tape outs with inductors in the Skywater 130 MPWs, but we couldn't find data or like actual measurements.
Yeah, it's still early in the day for data. How did you hand draw the inductors, or did you have a computer program generate them for you?
No, we used oh god, I forgot the name of the software, but we used I forgot the name, but we used one of these tools that can generate the .c.
Okay, that's interesting. I was under the impression that they didn't exist yet for inductors. Maybe you can send me when you remember it, you can send me a link and I'll put it in the description of the video.
I will. It's an open source tool and it works quite well. So one of our students was focusing on these, and he could generate different versions. He was checking the inductance estimation that the tool does with the manual calculations. There was some sort of matching, so we tried to move like this. We didn't go too deep in this part because we didn't have time. It was really at the last part of the design.
Yeah, so some of them look like they're not connected, so I guess that's true. You're just going to wafer probe them and test them on the die.
Yeah. So we had some of them connected to the pins, but most of them have their own paths, and there are also some structures to de-embed the parasitics. So try to
nice looking logos too.
Yeah, there's also part of the final tasks we could complete.
Yeah.
So
Okay. Is there anything else you want to show us from your deck?
We also had some simulations, efficiency simulations. So we stripped the output current, and we could get evaluate the input and output power, and from this get the efficiency. And we can see that we get the expected curves for these kind of systems. And we have this evaluation for the 1 megahertz version of the testing, the 1 megahertz testing mode, which includes the off-chip capacitors, and the 10 megahertz version, which is fully on chip, so no off-chip capacitors.
Okay. Nice.
And then we have also the dual core efficiency, and it's nice because we can see that we reach over 90% now. Also, as Weston noted in his measurements, this will not be the case probably because we have a lot of other parasitics and series resistances that we're not considering in our ideal simulations. So, but at least we can see that we have the possibility of going around 90 maybe here with dual core. That's what I would expect.
Kind of side question, and maybe you don't know the answer because we're talking about the right-hand side of that system diagram you drew. But on the left-hand side, where you're converting from the solar cells to the DC bus, is the CubeSat spinning? So do you get like these quick pulses in energy from all three axes, or are they slow? Like, do the DC converters need to be especially responsive? Sounds like quite an interesting problem.
A good question, actually. Because, you have also the CubeSat technology is evolving quickly. So I think currently there's a way of stabilizing the satellites, these small satellites. So they have thrusters and all, micro thrusters and these kind of things.
But, and the little spinning, what do they call them? Something wheels.
Spinning wheel, I think.
There's a good name for them. I've forgotten. People build like these cool balancing robots that use them.
Yeah, exactly. You have some mechanisms to do stabilization, but many of these satellites are just like very, very
fire and forget.
basic. Very dumb. So in that case, I think you would have this behavior. This,
okay. Yeah. Okay. So let's go back to this view. Maybe you can tell us. So we've got like a wait now for ChipIgnite to run through Skywater, get packaged, and then be sent out to us. What do you have in mind, and what are your plans for bring up and testing?
So yes, that's what we're trying to define now. Where we have some students who are focused on the testing part. They're designing PCBs.
And I noticed that your system is driven by an FPGA, so I guess you need that kind of that system built.
Yeah, exactly. So we need a main board which can get the boards with the chip connected, and also external instruments and FPGA. The first test, I think, it will be fully open loop. So just triggering some, sending some triggers, some signals, some gate signals, and trying to see if this matches with our simulations. And then we will
single cycle transients kind of things. Match it up with this device.
Exactly. Yeah. So we have some system simulations where we can get for the conditions that we're applying, we can get and for the output that we want to provide, the voltage, and for a load current, we get the duty cycles and all these kind of things, and then we can just code this very dumbly in the as input, digital inputs, and then we will move to hopefully to a closed loop version with an external control system. But for that, we need to figure out some things, because we need to measure voltages, we need to buffer, and we need to try to not affect the system with our measurements, right? So
you'd need to add like an external A to D. Okay. So maybe that's like if you do this again in the future, or do like the next revision, then that could be that A to D in the control loop could then end up being integrated.
Exactly, yeah. A to D or an analog loop, that could also be an option, like Weston did.
Okay.
Yeah. So also, we wanted to explore this high voltage, let's say 20 volt to 10 volt or 5 volt conversion. So we can also try to do this part, right? So look for topologies that allow flying or bootstrapping structures, there are capacitors that can charge the gates at these voltages without risking to break down the oxides. So that would be also a nice next step to follow. And also, try other topologies. We are working in a power electronics group, discrete power electronics. So you have these huge racks full of stuff, but they have a lot of different topologies and different applications. So we're trying to translate this power electronics language into the microelectronics world to see what makes sense and what could be a contribution.
Great. Really fascinating project. Thanks for taking the time to explain to us the process and what your design, what you came up with. If people are interested to get in touch with you to find out more or to follow your work on this, what's the best way people can get in touch with you?
Well, I use LinkedIn. I can also share my email.
Do you also say LinkedIn?
LinkedIn. LinkedIn. Yeah.
Aquí en España decimos LinkedIn.
In Chile, you would say something like LinkedIn. Like
LinkedIn.
we
Okay.
even pronounce less letters than. I think our accent is more similar to the Sevilla accent.
Okay.
So it's really
Right.
like no consonants whatsoever. So just vowels. I can also share my email. It's Jorge.
Maybe don't share your email, otherwise you'll get too much spam. But in the description of the video, we'll put a link to your LinkedIn profile.
LinkedIn and also GitHub, and
Yeah.
It's easy to find.
Cool. Okay. Well, thanks very much again for your time, Jorge.
Okay.
Really cool to talk to you, and a great project. Looking forward to reading the results when you publish them.
Great. Thanks a lot.
You're welcome. Take care.
Okay, you too.
Bye-bye.
Bye.